All right, let's continue on with a few more problems. I wanted to break this into a more manageable chunk so it wasn't so overwhelming to watch it all at the same time. So here we're going to look at a problem that has no values. We're just using variables. And it says we have a block sliding on a frictionless tabletop. Here's our table. And it's connected by a string that passes over a pulley. So here's my pulley. And here it is. And there's another mass down here hanging down. We want to find the acceleration of those masses and then the tension in the string. Before we do that, we need to set up our coordinate systems. We want the coordinate system to be in the same direction for each tension in the string. So each portion of the string, and I'm going to show you what I mean by that. For this one, this might seem obvious. We're going to put the x direction to be parallel with the tension here in this string. We want to do the same for the second weight, which means we're going to have to turn our coordinate system. So this time x is going to be facing downward, and we turned it, so that means y is in this direction. So we know tension is here, that's T, and we know this has weight. We know this also has weight, and we know there is a normal force. So let's see what we need to do. Let's think through this. We're looking for acceleration. So the first question we should ask, is there any acceleration in the y direction? No, there is not. We have no acceleration here, and we have no acceleration here. Everything is in the x direction because we've set our coordinate system accordingly. So that being said, we're going to ignore the y direction and let's look at what's happening in the x direction. Okay, so let's break this apart. We're going to look at the first mass and then we're going to look at the second mass. The first mass. What is happening in the x direction? So what are the sum of the forces in the x direction? Well, for mass 1, the normal force is in the y direction, so we can ignore this. The weight is in the y direction. We can ignore that. We only have tension. So the sum of the forces in the x direction is just T. And we know that the force is equal to mass 1 times acceleration. So that's equal to T. For the second mass, we have two forces acting in the x direction. We have tension and we have weight. So we're going to have 2. The tension is pointed in this upwards direction, which for our coordinate system happens to be negative x. So it's going to be negative T. And the weight will just be m2g. When we use the same system we did before, we're going to see that ma, that's m2a, equals m2g minus t. Now we have two equations. So let's use this simpler equation and plug it in so we can actually solve for A. In order to do that, we need to get rid of tension. So let's substitute T equals MA in for tension. I will choose a different color for this. Let's use blue. Okay, we'll do it over here. Actually, why don't y'all go ahead and try to plug that in and see what happens and play the video when you're ready. Okay, hopefully y'all have substituted this correctly and then rearranged correctly. So we have T equals M1A. So when we plug that in, we get M2A equals M2G minus M1A. Let's go ahead and gather like terms. And when we do that, we should see that M2A equals, M2A plus M1A. We wanted to get the acceleration variable on the same side, is equal to M2G. We're going to pull out A, and we have M2 plus M1 equals M2G. From there, let's rearrange one more time, and we'll see that acceleration is equal to M2G divided by M2 plus M1. Okay, so there is our acceleration. Now, we need to do part B, which is finding the tension. Okay, and y'all can try this one too. So instead of plugging in T to this second equation, you'll want to plug in A. So we want to rearrange M1A equals T. And I'm going to have to erase this because we have too much going on here. So we had M1A equals T, which means T is equal to A over M. I am so sorry. I don't even know what I just did. Which means that A is equal to T over M, and that's M1. We need to plug that into the equation. And when you plug it in, you should see M2 T over M1 equals M2G minus T. Just like we did with acceleration, we want to get the T's on the same side. And when we move them over, we're going to see that T plus M2 T over M1 equals M2G. Okay. Now we just need to rearrange this, and this might be the difficult part. So let's pull the T's out. So pull the T's out, and we get 1 plus M2 over M1 equals M2G. Rearrange this again, and we'll see that T equals M2G divided by, and I'm just going to rearrange this so that it says M2 in the front. It's the same thing. And finally, we can simplify this just a little bit more to find that T is equal to M1, M2 divided by M1 plus M2, all multiplied by G. So when you simplify that as much as we can, this is what you would end up with. Okay. We have a couple more problems to look at. Well, 3 more. And now we're going to look at a completely different type of problem. We're going to look at a roadway which is banked at an angle so that a car can go around it and not skid off the roadway. We want to find the angle for a car that's traveling at 20.5 meters per second, where there's a turn radius of 85 meters. So let's kind of sketch that out. There's my curve. Here's my radius, which will be 85 meters. There's my car. So my car is going to have a force going that way. It's going to have a force going in the direction it's moving. We know mass. Why am I rewriting? We know mass. And we know our velocity. Okay. So if the car is turning, we know there's a force pointed toward the center of that circle. So we're going to set our coordinate system like so. X, and Y. X is pointing towards the center. Or the x-axis is pointing towards the center. So the force is pointing in the x direction, the force that keeps this car from skidding off the road. The weight part is only in the y direction. However, and this is very difficult to visualize just because I don't know how to draw a banked angle. So I hope you're able to visualize this in your head. Here, maybe I should draw it more like this. Yeah, that makes more sense. Okay, here's my car. So we're going to have a normal force. Remember, it's perpendicular. And your force of weight is still with the road. So the weight part is in the y direction. But since this is a banked road, that normal force is, and the normal force is perpendicular to the surface, the normal force is going to have an x component this time. So it's going to have both. All right. So that's necessary to keep the car in the turn. So we need to find all those forces in the x direction and all of them in the y direction. Just like we've been doing. This car does not have any movement in the y direction. So we know that whatever it is that's happening in the y direction is going to result in a net force of 0. So whatever is happening there, they're going to cancel each other out. We know that our weight has a y component, and we know that the normal force has a y component. So the sum of those forces is 0 equals the normal force in the y direction minus the weight, which y'all know is mg. For the x direction, we don't have a weight component in the x direction. We just have the normal force. So the sum in the x direction is just going to be a result of the normal force. Let's go ahead and substitute where we can. Okay, we can replace the force with max. But since this is circular motion, we know that that's actually going to be centripetal acceleration. We've seen that in an equation before, so we can go back and look at our equations. And we're going to use this one. Okay. And then we can make another. Oh, I'm sorry. We haven't gotten to the equation part yet. We have ma centripetal equals, and because this is in the x direction, it's going to be in sine theta. Now we're going to use that equation, and this is going to get replaced. It's going to be mv squared over r is equal to n sine theta. Over here in the y direction, let's go ahead and replace this component. It's going to be 0 equals n cosine theta minus mg. We can rearrange that, and we can actually see that the normal force is equal to mg divided by the cosine of theta. We want to solve for the normal force so that we can plug it in over here. Why would we want to do that? Well, we are trying to find the angle, and we need to work with the information we've been given. We have velocity, we have the radius, we have the mass. So this will be quite easy to go ahead and find theta now that we have n. I need to erase again. Okay. Let's make our substitution. So we have mv squared over r, that is a squared, is equal to mg divided by cosine theta times the sine of theta. We can cancel out a couple of things, so let's go ahead and do that. Our masses are going to cancel. And that is going to lead, and then we can rearrange. Let's get rid of the fraction. Let's take r over here, and let's move cosine. So that's going to be r cosine theta. No, I'm sorry. V squared cosine theta equals r sine theta. Need more space. We can move the sine and the cosine to the same side, and we can use the fact that sine theta over cosine theta equals the tangent of theta to our advantage. So we'll see that v squared, did I drop the g somewhere? Yes, I did. There should be a g there. V squared over gr equals the tangent of theta. So to solve for this, we'll rearrange a little bit more, and we get that to find theta, we're going to need to use the inverse tangent of v squared over gr. That will allow us to solve. And when you plug in all your numbers, you should find that theta is approximately 26.7 degrees. That's the final answer. Oh, we only have one more problem. Almost at the end. Okay. Final. Oh, I had an image for you. I hope that image made it a lot clearer what was happening. I apologize that I forgot to use it. In this one, we're looking at a centrifuge, and this last one is going to be incredibly simple compared to all the other problems we've been doing. It's rotating, we see its linear speed, and we have a measurement here. We have the radius. It's in centimeters, and we see that speed is meters per second, so let's make sure we also know what this is in meters, which is 0.0925 meters. If you look at the equations you now have, you should see that we have an equation that's going to work perfectly with this. It is the centripetal acceleration is equal to v squared over r. We used it in the previous problem, but that problem was far more complicated. This one is extremely straightforward because we have that velocity and we have our radius. Let's just plug in our information, 90.6, that's squared, and divided by 0.0925 meters. When we solve, we'll find that it is 88700. That's meters per second squared. So if we converted that into G's, that'd be about 9,000. But you don't have to worry about doing that. I just wanted you to be able to find the acceleration, which is 88,700 meters per second squared. So that is it for working problems in this chapter. Be sure you try some of those study guide questions before attempting your quiz. And if you feel good about those, the quiz should be quite simple. If you need extra assistance, reach out to me and we can set up a time to meet. And otherwise, y'all have a great day. I'll see you next time.